All right, now let's talk about some unusual points, and these points are going to have an effect on the correlation coefficient, which makes them unusual. Now remember back to lesson 2, we said the only thing that really changes the correlation coefficient are departures from linearity. So we're going to talk about a few of those today. Now the first one is an outlier, and this is a data point that falls outside of the general linear pattern of the data. This point also tends to have the largest residual and tends to be the furthest from the data. So that's just going to be like an unusually high output or unusually low output when compared to all the data. So if this is like my straight line, it's going to fall down here or somewhere up here, but it's just outside of that pattern. Now a high leverage point is a data point that has an unusually large or small explanatory value that tends to shift the general trend of the LSRL towards that point. So let's assume here's my straight line and I've got a point that again, doesn't follow the pattern. It's kind of down here. It's going to shift my line to accommodate that point. So that's going to weaken my correlation. And then lastly, we have an influential point. And this is a point that, if omitted, it would greatly affect the strength of the LSRL. Generally, these points follow the general linear trend of the data, and high leverage points or outliers could be considered influential depending on their location in relation to the rest of the data. And then lastly, if you're predicting a response value for an explanatory value, variable that is beyond the domain of the data used to construct the LSRL, this is called extrapolation. And this is just like if I gave you data from 1990 to 2010, and then you try to use that model to predict 2020, 2030, etc. That's not going to be the most accurate because my data was only valid in between that time frame that I gave you. So predicting outside of that realm is not going to be the most accurate. We call it extrapolation. So these are just some cases here of things you might see when dealing with these unusual points. So suppose we've collected the following data for two quantitative variables. We've got our x and y, and we've got our scatter plot here. You can see that we have a strong positive linear relationship. So let's go ahead and compute the correlation coefficient. And this is what I didn't touch on in the last lesson. So here, notice my slope is positive, so r is also going to be positive. And I need to take the square root of 0.965. So my correlation coefficient is going to be about positive 0.9823. So that's going to be a strong and positive linear association between the two variables. And look, I'm already answering all my own questions. You can see here it kind of just gets in, you just kind of get into the practice of them, saying them enough times. So here, there appears to be a strong, positive, and linear relationship between x and y. There appear to be no unusual points or observations yet. All right, and then lastly, let's calculate the residual for an explanatory variable of 5. Is this an over or an under prediction? So here's my model, and we can see here at 5 I have an actual of 11. So let's take, sorry, kind of hiccup burped, I don't know. All right, so let's find y hat of 5, which I'll find by substituting this into the model. And 1758 times 5. That's going to give me a predicted response value of about 11.8123. So to find the residual here, I'll do y minus y hat, or 11 minus 11.8123. Again, I'm going to get a negative residual value, but notice that even though it's negative, the actual value is 11, and I predicted 11.813. So this one was actually an over prediction. So the LSRL over predicted the response variable by 0.8123 units. So you can see all of the connections here that we've been making. All right, so let us now take a look at what some of these unusual points might be. So here's our first unusual point. Now the data point is added, and this one's got 530. And notice that my original y-intercept was 0.933, so that's increased. My slope has decreased, my standard deviation has increased, and my coefficient of determination has decreased. So let's go ahead and compute the new correlation coefficient. I'm just going to take the square root here of 0.531, and it's still positive, so my new coefficient here, correlation coefficient, now becomes 0.7622. So this is decreased. So let's take a look here at some things that have changed. My correlation coefficient is decreased. my standard deviation has increased, my coefficient of determination decreased, slope decreased, and my y-intercept has increased. And all of this I've just observed through the various computer outputs. Now let's calculate this residual. So here we've got y hat of 5, and if I were to substitute it into this new model, I'm going to get an output of 13.5109. So my new residual becomes y minus y hat of 5. So my initial 30 minus 13.51 is going to give me a residual of positive 16.49. So we are definitely under predicting because here's the actual data point and we predict it to be way up here. So this is going to be a large residual. When it's a large residual like this, we call this an outlier. So this is an example of an outlier that you might see. So next up, let's suppose that 11th data point is actually here at 1515. And again, let's note the changes from our original data set here. So now to find the new correlation coefficient, I'm going to take the square root here of this r. And so that's going to give me 0.7622. And whoopsies, I think I definitely made a boo-boo here. I was just going too fast because I was so excited about my unusual points. So this r should actually be 0.7287. You know, it's really hard to teach to an empty classroom in the middle of the summer. Okay, so here's my new correlation coefficient, 0.7622. What is unusual about this point? Well, we can see that a majority of the data was right here between 1 and 10. So this is outside of the domain. But aside from being outside of the domain, it's also outside of the linear pattern. So let's note some changes that we see here. So from our original computer output, the correlation coefficient has decreased, which means my coefficient of determination is going to increase. My standard deviation of the residuals has increased, and my slope decreased, and my y-intercept increased. And again, I'm just referencing the original computer output there on page 10. So this point out here, it's outside of the domain. It's affecting the correlation coefficient and the coefficient of determination. It's outside of the pattern. This is an example of what we call a high leverage point. It's got an unusually small x or large x. So since 10 is like the last notable x that I have, 15 would be considered quite outside of there, right? So high leverage here. Could also be considered influential depending on its effect on the coefficient. And I think definitely this could be high leverage and influential. But now let's talk about this last one here. The 11th data point is going to happen at 3060, way outside of what our data was given to us as. So this is way outside. You can see that it actually increases the coefficient of determination here. So let's find our new let's just go bright blue here. So our new r is going to be a positive, and then we'll take the square root of this. So it's actually going to be 0.996. And now that I'm writing this out, I don't really like that color. So sorry to all of my neon blue fans. Let's find a happy medium. All right. So here we've got positive 0.996 increased from our original 0.9823. What is unusual about this point? It is, well, first off, it's out of our domain, but it follows that linear pattern. And I would say pretty dramatically, like you see it's way out there and it's increased our coefficient of determination and our correlation coefficient. So this here is what we call an influential point. And using our model to predict such a point, this is also an example of extrapolation. We're extrapolating based on a small data set on what we believed to remain true. Now, we're going to see here that it actually increases our coefficient of determination and our correlation coefficient. It relatively increases our standard deviation, not by much. It's going to decrease the slope to accommodate that point, and then it's also going to increase the y-intercept. So really what's important to note is these three summary statistics. The slope and the y-intercept are going to change depending on where that point is located from the original data set. So shifting it up is probably going to shift the slope up and then decrease the y-intercept, and shifting it down is going to decrease the slope as well as shift the y-intercept up. So you'll kind of see that relationship there throughout all of these three unusual points here that we've seen. So what I need you to do now is I'm going to need you to pause lay video and go ahead and look at these examples here. So this one talks about what happens when we have this unusual point in the data set. And then this one is just good old true or false, which is a very popular component on the AP exam. So go ahead and pause the video and try out these example problems for yourself. So good luck. All right, so hopefully not too challenging here, but you can see that the change of just one slight word changes the entire interpretation. So a point with a large residual is an outlier. That is totally possible. However, an outlier is typically the largest residual. A point with high leverage has a y value that is not consistent with the other y values. False, we're looking at extreme x values here. And the removal of an influential point can change the value of the correlation coefficient. Most definitely true, that's what we've talked about. So we should get false, false, true. Now, I do like this question, and it has shown up on previous AP exams, but suppose we have a scatter plot relating height and arm span, both in inches, and we have point A. So red would be the LSRL if A is removed, and blue would be the LSRL if we have that A point included. So if A is left in the model, and we can see that our LSRL is going to shift, then our correlation coefficient, our coefficient of determination, and slope are all going to decrease, and the standard deviation of the residuals will increase. Whereas if we remove this point, then the opposite is true. Now our strength should improve, which will improve the correlation coefficient and the coefficient of determination. The slope will be adjusted, and then our standard deviation is going to decrease. Since the line is now following a majority of the data, we don't have too much extreme variation going on there. Now this point in the green at 68.72 inches right here, we can see that it's kind of far off from the data regardless if I use the red or the blue, so that one would be considered an outlier because it's got the largest residual. Here in the purple, 90.90. If I put it way out here, again, regardless of whichever line I'm using, the line's going to shift to accommodate this point here, so that would be considered an influential point. And then lastly, would it be appropriate to use the model to predict an arm span of a student who is 48 inches tall? Well, we can see here that our data pretty much ranges from like 60 to 72 inches. We'll just assume we're removing A for now. So no, it would not be appropriate to use our model to predict an arm span of a student who is 48 inches tall, since the heights used to construct this LSRL range from about 60 to 72 inches. Making such a prediction would be considered extrapolation. So again, I'm giving my answer, no, my context, the height and arm span, inches, some values, and then I'm explaining that doing so, it would be extrapolation, and because it falls outside of the range here. So again, to ace our answers here in AP Stats, we answer, context, explain. So that's going to wrap up our lesson here on unusual points. And now we've got all of our interpretations and all of our components for linear regression. So in the next lesson, we're going to talk about computer output and putting it all together in a model. So stay tuned.